so a bit within subject. So let's just see if we can wrap some things up here. That we're looking at both the orbital period for a satellite. Is there a way that you can calculate the period of a satellite? And secondly, what's the energy that a satellite has because of where it is? So those two things are what we're going to cover this morning. So if you've got a planet, like that there, and you've got a satellite orbiting it at a particular distance, r measured away from the center of the planet rather than the surface. This is going to be important. That you need to remember that when you're measuring distances with gravitation, it's always from the center of the object rather than from the surface of the object. If we say that a satellite has a mass small m and the planet has mass capital M, we should from that be able to work out the time that it takes the satellite to go around the planet once. That's the orbital period, t. So the time for one revolution of the whole planet. Different satellites orbit at different times. What, from standard grade, you should know what affects the time that it takes for one satellite. Yep. Okay. So the distance that you are from the planet. You might remember a wonderful bit of software on the BBC, which is yet to be surpassed, which showed you that as you increase the radius, you increase the period of time. So can we actually show that with what you know both from gravitational force, and from central force? So we're after that period there. What actually holds the satellite in orbit? Why does the satellite not just carry on into deep space? It's going quite fast as it's going around the planet. What actually keeps it there? Okay, Alistair? Okay, so we've got a force here due to the gravitational attraction between the two. What's the equation that relates the force? Really, it's commonly called the weight, but even out in space, you could just call it weight. What equation would you have for that force between the two? Big G. Yeah. Mass of the planet times the mass of the satellite. It is r squared because it's the force. Chris mentioned negative. It's not negative because it's just the force, not the energy. So that's the force of attraction between the satellite and the planet, and that's why it stays there. It stays with the planet rather than shooting off into space. What force does that actually provide? Okay, so that's our central force. So that force, the gravitational force, is equal to the central force, and the central force for this going around like that. Let's just see if we. Good morning. If you've got the radius there, and you've got the time for the radius. Sorry, you've got the time to cover one complete circumference. You should, from that, be able to work out what the central force would be in terms of all the things that I've got there. What are we going to need to work out using period of rotation and the radius? Yeah, no? Yeah, so we could do either. We could either say that we can get the linear speed of it, v, which is going to be equal to the circumference, 2 pi r, divided by the time for one revolution. That will give us v. What else could you work out, Anna? Okay, so we could get omega. We could say that omega is 2 pi 1 revolution times the time for one period, capital T. And we're going to put that into the equation for central force, which we'll take a vote on it. Would you prefer to work with V or omega? It depends on the day of the week as to whether I work with omega or V. Also, it would depend on the information I'm given in a question, but in this case, you decide. For the camera, the class are looking like stunned mullets at the moment. Oh, it's going to be close. It's going to be close. We've got 5 for omega, 6 for omega. Okay, then. And for V, who would want to work with linear speed? 1, 2, 3, 4. The omegas. Oh! Manella had a casting vote from the cameraman. Nope, it's actually... we're actually going with omega. just for the Greek freaks here who prefer working with Greek letters than those ones there. So we're dealing with the central force, equation for central force. It is, okay, so we're using mr omega squared, putting in that omega is 2 pi over t, so we've got mr 2 pi over t all squared, and that's going to be our equation for central force. And because the central force provides, because the gravitational force provides the central force, then we can equate the two. So we can say that G m for r squared is equal to mr 2 pi over t all squared. From that, you should be able to work out an expression for t in terms of everything else that's there. There is one nice thing, though, that you should be able to spot immediately before we'll go any further. Oh? Yeah. Because mass appears on both sides of that equation, because the gravitational force is proportional to the mass and the central force is proportional to the mass of the satellite doesn't affect the time that it takes to go around the planet. It's only the radius that it is away from it. So the International Space Station is going to orbit at the same time as a bit of sort of space junk which has fallen off it. So the orbital period is only affected by the radius. But that's one thing which we're getting from this. So can you rearrange this to get what t is in terms of everything else there? Taking the t squared over to this side, you'll have t squared on this side. R squared at multiplying r becomes r cubed. Gm, capital M dividing on that side. And the 2 pi squared, so it's 4 pi squared over here. Now, because you're taking the square root of all that to get what t is, you'll actually end up with 2 pi times the square root of r cubed over g times m. And that's the equation there. I would not recommend that you go in, learn that, because one, it'll confuse all the other equations that you're supposed to have learned already. And secondly, it's so easy to derive, and generally the question is about the derivation rather than than just learning it and applying it. So the key things to think about are what provides the central force is the gravitational force, and we're equating those two forces to get that equation there. So I'm not going to put that in a box and ask you to learn it, but that's what it is there. Okay. So the next thing you need to be able to work out is what the energy of a satellite is. That's kind of an easy thing, you think. So if you've got something, planet, satellite, orbiting it, going around like that, what kind of energy is it going to have? Well, it's got certainly rotational kinetic energy. Well, it's got kinetic energy just by virtue of the fact that it is moving, that it's got this linear speed at any particular point, half mv squared. So the kinetic energy is going to be half mv squared. You could express that as being the rotational kinetic energy that it's got because it's just a single point mass going around the planet. It would also have rotational kinetic energy if it was spinning at the same time. A lot of our satellites, the early satellites, actually spin to keep themselves in a sort of gyroscopically stable state as they're going round. So they do have an element of spinning to them as they're orbiting. But the main kinetic energy is just the linear half mv squared. If it's going at v at any particular time and it's got a mass, then it's got a kinetic energy. Because of where it is, though, from the planet, at this radius r away from the center of the planet, what other energy will it have? Right? Okay, so it's got this gravitational potential energy, and this is what you've done with Mrs. Monroe, that if you plot gravitational potential energy, what's the general shape of that graph of potential energy for something in space as you change the distance that you are away from the planet? Stars, what would that? graph look like? You go like that? Okay, so we've got a curve going like that there. And it is this curve, and you're right, it is negative. It's going from the bottom. What's the thinking about, well, let's just to recap on this. Why do we use zero potential energy out at infinity, which is where you're leading off to? What's the thinking behind that? Okay, so if you're anywhere near a planet, there is going to be some gravitational field, so you are going to have some energy. Why do we use zero, our reference point, at being infinity? Why not just the surface of the Earth? Huh?
Because gravity varies on different things, so like if your poles is different from the equator.
Yeah, that's very true, that because of the spinning of the Earth, then you've got different amounts of gravitational field strength, so that would make your potential energy different. Why in physics, why in sort of astrophysics do you say that, right, at infinity, the potential energy is zero? Why not just say it's zero at, say, ground level in Inverness? Yes, you might be sort of above, what do you say, well, there's going to be ground level at sea level. All the time you're dealing with differences in what you're setting as your standard, your reference. So the potential, to say that you want zero potential energy, the easiest way was to say that we're dealing with zero out at infinity. The equation that relates potential energy from that radius, what was the equation? You just covered this on Tuesday again, Don. Gm over R. So that's the gravitational potential, and that means that at any point at a distance r away, there is the potential for something to have energy. What is it the object got to have to actually give it the energy, though? That potential energy at that point. What do you need to put in that equation? Yeah, Alistair, what would I sort of multiply that through by to work out what the energy is? If I've put a mass there, clonk, at a point that has a gravitational potential, what would I need to know to get the energy that it's got at that point? Yeah, so I'd multiply through by the mass, so we've got minus gm over r. And so the potential energy that satellite has got is negative gmm over r at that particular radius. You can actually add the two together. This is always going to be positive. Kinetic energy, because v squared is always positive, this is always going to be negative. And you can actually combine the two. So let's just think how we could do that. Let's go for the kinetic energy. So the kinetic energy, Ek, plus the potential energy is going to be half m v squared minus gm over r. It's looking like a complete dog's breakfast there. We've got v, we've got m, we've got m, we've got r. Ugh, yuck. There is a way that we can simplify it, though. Can we get v in terms of everything else that's in the equation, but not v? There is a way. So I'll give you a couple of minutes. Can we get v and replace v by things like g, mass of the planet, radius, things like that? Right, so the last bit we've got equating the central force in terms of linear speed and gravitational force, mv squared over r equals gmm over r squared. That cancels with that. The mass cancels with the mass there. So you can replace v squared by gm over r. So this equation here becomes half the mass times g capital M over r minus gmm over r. Sorry? You get minus a half of gmm over r. And that's the total energy for a satellite, no matter what height it's orbiting at, by the time you add the kinetic energy and the gravitational potential energy, you always get that value minus half GMM over R. And it's always negative. So a satellite will lose more and more energy the closer it comes to the Earth, even though it's speeding up.